Hi everybody! So in this video we're going to take a look at some different mineral samples and how we can use a polariscope in order to identify them as either isotropic or anisotropic. Some of the experiments we're going to do today are derived from the previous educational videos on optical mineralogy isotropic materials and optical mineralogy anisotropic materials. Feel free to follow the links to check them out. So in order to follow along with these experiments, you'll want to purchase the isotropic versus anisotropic kit from Snellius Minerals. Snellius Minerals is an eBay store currently located at the following address. Check out the other nerdy minerals while you're there as well. Unless you happen to have a nice spinel, tourmaline, calcite, and fluorite crystal laying around, in which case you can kind of make your own. So in our previous video, we talked about linear polarizers, which are necessary components of a polariscope. We went through a bit of the history behind these polarizers and how we can actually create a polariscope from them. And so to actually utilize the isotropic versus anisotropic kit, you're going to also need a polariscope. So hopefully you either have a polariscope or you can buy the linear polarizers from Snellius Minerals and make your own. And there are more detailed instructions for creating your own polariscope in the video Snellius Minerals DIY Polariscope. My polariscope that I'm using in these videos simply consists of an LCD screen, in my case an old iPad, and an upper polarizer, which is just a linear polarizer I've oriented appropriately. So let's take a look at my polariscope. Here you can see this screen. This is just the screen of an old iPad. And so the light we're seeing is actually currently plane polarized. And it's plane polarized in this instance in a north-south direction. So this is one of the two most important viewing configurations we'll have for our polariscope, and with it we'll be able to transmit plane polarized light through our minerals. Our other important viewing configuration for our polariscope involves an upper polarizer. And this upper polarizer is oriented so that the vibrational direction of light that would be allowed to pass through it is actually perpendicular to our initial plane polarized light. As such, no light ends up passing through it, and it appears dark in this image. So that you can tell I'm not up to any chicanery, we'll rotate the upper polarizer a bit, and you can see that light is allowed to pass at different orientations when the vibrational direction of our upper polarizer matches with that of the plane polarized light we are generating from our LCD screen. But our upper polarizer is most useful to us when we have it in this configuration where we have crossed polarizers and no light being transmitted. So more schematically, our two important viewing configurations are going to be viewing our minerals in plane polarized light and then also viewing our minerals with crossed polarizers. So let's get to the fun stuff now and take a look at some of the minerals in our isotropic versus anisotropic kit. And we're viewing this in just normal everyday light. There's nothing weird going on with our lighting configurations here. So the kit is going to consist of a spinel crystal, a tourmaline crystal, a fluorite crystal, and a calcite crystal. So if you already have these minerals, you can do these experiments on your own. The one thing with the kit, however, is that I do actually test all of these beforehand, and these crystals actually have to be fairly high quality. You don't want too many inclusions in them, or else it's going to start bouncing the light around and you're going to get weird results. Because the crystals have to be high quality, this is also why the spinel and tourmaline crystals in particular are quite small. As soon as you start to get to larger and larger crystals, they become more and more expensive, and so that's not really great for trying to make a low-cost educational kit. So just beware if you're using your own minerals, you might have some weird things going on just depending on how included they are. Or also if your mineral happens to be twinned. So the real benefit of the curated isotropic versus anisotropic kit is you don't have to worry about any of those other things that may be going on. With that all being said, the first experiment we want to do here is actually not going to involve our polariscope at all, and it's going to use our fluorite and calcite crystals. So we are also going to make use of a single linear polarizing light filter as well for this experiment. So if you don't have any of those, you might want to pick up the pack of linear polarizers from Snellius Minerals. We'll start by taking a look at an image through our fluorite and calcite crystals in normal everyday light. And so here we have a bit of writing, and what we're going to do is bring our fluorite crystal in and view the writing through our fluorite crystal. And to be honest, nothing really that interesting is happening when we're viewing this writing through our fluorite crystal. The image is a bit distorted because the cleavage faces of our fluorite that we're actually viewing this image through are not perfectly flat, and the fluorite also has some inclusions and cleavage traces in the structure which are also distorting the image a bit. So let's take a look at our writing now using our calcite crystal and see if there are differences between that and the fluorite we just looked at. So as we start to view the writing with our calcite crystal, you can see that the image is actually doubled. And this image doubling is our first hint that there's something very different going on between the optics of our fluorite crystal and the optics of our calcite crystal. So let's rotate our calcite crystal now and see if we can notice anything interesting about our two images. So as the calcite crystal begins to rotate, what I want you to notice is that one of the images appears to circle around the other image. So these two images are each given their own name. The image that's staying in place is called the ordinary ray, and the image circling about that is called the extraordinary ray. So I think this was enough spinning that we get the idea of what's going on here. We can learn something further about these two images though if we bring in a linear polarizer. When we bring in our linear polarizer, what I want you to notice is that one of these images is much more faded than the other. And as we begin to rotate our calcite crystal, what you'll see is that at certain orientations of our calcite, I can make one or the other ray completely disappear. So what this is showing us is that our ordinary ray and our extraordinary ray are actually both plane polarized, and they're plane polarized in mutually perpendicular directions. So with every 90-degree rotation of our calcite crystal, we go from the extreme of seeing only one ray to seeing a mixture of the two rays at intermediate locations, and then once reaching 90 degrees, we'll see only the other ray. So this experiment is showing us that light traveling through a fluorite crystal is going to behave very differently than light traveling through a calcite crystal. And the reason for this is because of the structure of our calcite and fluorite respectively. But we'll save a deeper dive into those concepts for a bit later video. Right now, what you need to know is that our fluorite is isotropic, whereas our calcite is anisotropic. In the case of isotropic fluorite, the direction that light is traveling through our fluorite crystal doesn't matter. However, with our anisotropic calcite, the direction light is traveling through calcite is actually going to matter. When light travels through our fluorite crystal, it does so in a relatively straightforward manner, whereas when light travels through our calcite crystal, it's actually going to be split into two different rays that end up vibrating in mutually perpendicular directions. And because of these differences, the behavior of our isotropic and anisotropic substances are very different when we look at them with a polariscope. There's actually a lot more going on here, particularly with our calcite. And so if you want a deeper dive, I'd suggest looking up this article. And I've also got another educational video on calcite crystallography, which can help you understand more about what's going on with our calcite. The link to that is here. With that all being said, let's take a look at the spinel and tourmaline from our kit using transmitted plane polarized light. So just to remind you, that's using this configuration of our polariscope. And also, we're going to be a bit more zoomed in than we were earlier, so the crystals appear larger than they are. So when we're looking at these crystals in plane polarized light, the phenomena we're going to try to observe is known as pleochroism. And the way we're going to observe this is by rotating our crystals while transmitting plane polarized light through them. So let's see if anything interesting happens when we spin our spinel crystal. And so as we rotate the spinel crystal in this plane, I want you to notice that not really anything's happening. We have this nice red color going on, and that's about it. I should also mention that all the crystals in the isotropic versus anisotropic kit are indeed natural, and in fact this spinel crystal also has an inclusion, and I'm not sure exactly what this inclusion is, but you can certainly see it right here in the crystal. and this will be useful to us a bit later. Well, overall, spinning around the spinel was pretty boring, so let's get rid of that for a moment, and now let's focus on the tourmaline crystal. So as the tourmaline crystal rotates in plane polarized light, we see a completely different behavior. It goes from a lighter yellowish green color to almost completely dark with just a hint of light coming through the crystal. As we continue the rotation of the tourmaline, it returns back to that lighter yellowy green color, and then further rotation of the tourmaline crystal can take us back to the almost completely dark position that we've seen before. And with further rotation, we can take the crystal back to its initial starting position and the initial starting color of light yellowy green. So our tourmaline crystal has shown us the phenomenon of pleochroism with rotation in this plane polarized light. The spinel crystal has not. And observing this pleochroism is important because it lets us know that the tourmaline is anisotropic. If we see pleochroism in a material, that means it is anisotropic. And for a material to be anisotropic with respect to light, it simply means that light is going to interact with the material differently in different directions. Hence, seeing the change in color of our tourmaline crystal with rotation of the tourmaline crystal in plane polarized light is indeed telling us that the tourmaline is anisotropic. So for our materials that are anisotropic with respect to light, the viewing direction through our crystal is going to matter. For materials that are isotropic with respect to light, that viewing direction doesn't matter. Their interaction with light is the same no matter how we're looking at them. That sounds suspiciously like the spinel crystal not showing any pleochroism, doesn't it? With our spinel, however, we'll need a further test with our polariscope before we can confirm that the spinel is isotropic. So it's also an important thing to note that seeing pleochroism is diagnostic that a material is anisotropic. However, not seeing pleochroism is not diagnostic that a material is isotropic. So let's take a look at our spinel and tourmaline crystals using our other configuration for our polariscope where we have crossed polarizers. So in order to do that, we'll go back to our view of our spinel and tourmaline crystals in plane polarized light, and we'll bring in our upper polarizer, which is going to render everything fairly dark. Except you can see just a bit of light being transmitted from an inclusion in our tourmaline crystal, and you can also see a bit of light being transmitted along the edges of our spinel crystal. So it's important to note that when light reflects off a surface, you can actually change the polarization direction of the light. And so in this case, angles in our spinel crystal that aren't actually at 90 degrees to our viewing direction are what's bouncing this light around and causing a little bit of it to shine through. But what we're interested in here is not the behavior of little particular zones of our crystal, but instead the entirety, the gestalt of what we're looking at. And at this moment, both of these crystals would be called extinct. They're not really transmitting any light with our crossed polarizer view. But that's going to change here when I start to rotate our tourmaline crystal. So as I start to rotate the tourmaline crystal, you can see here it begins to transmit light. As I rotate the tourmaline crystal further, we go back to extinction. And as we continue to rotate the tourmaline crystal, you should notice a pattern of when the crystal is extinct and when it is brightest. So something to note, the light we're seeing here is technically an interference color. However, because our tourmaline is so thick, the interference color just ends up looking like white light, and interference colors are therefore much more useful to us when we're looking at thin sections, not so much when we're looking at these larger crystals. But we've seen now how tourmaline behaves with crossed polarizers. We have this pattern of extinction and transmission of light as we rotate the tourmaline crystal. Let's see what the spinel's going to do. So as we begin to rotate the spinel crystal, you can see that, well, it stays pretty dark. And the little bit of light you are seeing is from reflections off surfaces, changing the polarization direction of the light. And also you can see that fun little inclusion we were talking about earlier right here. So the view with crossed polarizers can sometimes help us identify things we might not see under other lighting conditions, and can be helpful in identifying things like inclusions. But back to the bigger picture, What I want you to recognize here is that the spinel and the tourmaline are behaving very differently with crossed polarizers. The spinel as a whole is staying extinct as we rotate the crystal with crossed polarizers, and this behavior is characteristic of isotropic materials. The tourmaline transition between extinction of light and transmission of light with rotation, and that kind of behavior is associated with anisotropic materials. Now for all the fun caveats. An isotropic material can actually transmit light with crossed polarizers if that material is under stress. And our anisotropic materials actually have up to 2 viewing directions where they'll behave like an isotropic material. These are known as optic axes and are going to be important in our identification of anisotropic materials. So because of these caveats, it's always important that when we view our minerals, we view them through multiple different directions using our polariscope to ensure we're not looking down an optic axis of our crystal. But in doing that, we're also going to have to be careful because as soon as we start moving things around in 3 dimensions, you're also going to have to think a bit about Snell's law and those internal reflections and such that are changing the polarization directions of our light. But for today, since we're just starting out, let's leave some of that complication behind. And if you want to understand better all the deeper theory about what's going on here, I suggest you check out the optical mineralogy playlist shown here. This goes into depth about a whole variety of different topics. But for now, let's just try a quick explanation of why we're seeing what we're seeing with our spinel and tourmaline. So going back to plane polarized light, we have our spinel and tourmaline crystals, and I want you to recall that the vibrational direction of our plane polarized light is occurring in a north-south direction here in this image, and our spinel crystal is isotropic. And another way to think about this is that an isotropic mineral only has one refractive index. And so if we want to think about a diagram to represent that refractive index as we're looking at our spinel, for this singular viewing direction through our spinel, it would be a circle with a radius of refractive index n. And so what effectively happens as we rotate our spinel in plane polarized light is that plane polarized light is always interacting with refractive index n, and well, nothing really interesting happens. We don't have any pleochroism. And when we go over to viewing our spinel with crossed polarizers, the spinel effectively stays at extinction no matter the rotation because there's no reorientation of the light. Once again, because the light is only ever interacting with one refractive index n. Things get more interesting, however, when we look at the tourmaline, which is an anisotropic material, and in this case our tourmaline is going to be defined by 2 refractive indices. And so taking a look at the tourmaline crystal in plane polarized light, we have the following pattern. And what I want you to notice is that there are 2 end-member colors. One color is a light yellowy green, and the other is pretty much completely dark. Once again, our plane polarized light in this image is vibrating in a north-south direction, and that's important for our color scheme here. If the plane polarized light were vibrating in an east-west direction, the color scheme would just be changed by 90 degrees. So our tourmaline crystal is showing us pleochroism, and let's go a bit more into theory to explain why that might be. Our tourmaline crystal is defined by 2 refractive indices. We'll refer to these as epsilon and omega. And the shape to describe these different refractive indices would actually be an ellipse in this particular viewing direction for our tourmaline with axes of epsilon and omega. In the case of tourmaline, epsilon is less than omega, and so that will be the shorter axis of our ellipse. So our pleochroism is actually explained fairly simply by thinking about the crystal in this way. When our plane polarized light aligns with epsilon, we see the pleochroic end-member color associated with epsilon. When the plane polarized light aligns with omega, we see the pleochroic color associated with omega. And everywhere in between is a mixture of these 2. Switching over to examining our tourmaline with crossed polarizers, we only see light when our plane polarized light is not aligned with either epsilon or omega for our tourmaline crystal. When aligned with either epsilon or omega, there's no reorientation of our plane polarized light, and as such, it just gets blocked by our upper polarizer, and our tourmaline appears extinct. But when our crystal is in orientations where our plane polarized light is going to be interacting with both epsilon and omega as it travels through our crystal, we can think of the light being split into two separate beams, one of which is going to travel more quickly through the crystal than the other. This is what's producing the light that we're seeing, which is actually an interference color. With our tourmaline crystal being as thick as it is, though, the interference color just appears as white light. So a quick recap of everything. Our spinel crystal is isotropic. And because our spinel crystal is isotropic, it's not going to exhibit pleochroism, and it's also going to stay extinct when we're viewing it with crossed polarizers. And this is part of the definition of being isotropic. Because spinel is isotropic with respect to light, it doesn't matter the direction light is traveling through the spinel crystal, it always interacts with the spinel in the same manner. This is also manifested as spinel only having one refractive index. This is very different from tourmaline, which is anisotropic. Because tourmaline is anisotropic, it matters the direction light is traveling through the crystal, and this is responsible for the pleochroism that we see in plane polarized light and the extinction and transmission of light that we see with crossed polarizers. And this is also then why tourmaline is defined by two refractive indices. Let's return to our fluorite and calcite crystals from our original experiment now and look at them using our polariscope. So right now we've got our fluorite and calcite crystals in plane polarized light, and let's rotate these around a bit and see if we notice any pleochroism. So our fluorite isn't showing us much of anything interesting. Let's try out the calcite now. And as we rotate the calcite, not really much of anything happens here either. So now it's important to remember, just because we don't see pleochroism doesn't mean that these aren't actually anisotropic substances. Our definitive test to distinguish these will be looking at them with crossed polarizers. And as I bring the upper polarizer in, you can see a distinct difference between our calcite and the fluorite. We of course need to rotate our minerals to be sure of what's going on here, and as I rotate the calcite, it goes from transmission of light to extinction, and back to transmission of light. So for our nice calcite crystal, we've pretty much confirmed that it is anisotropic. So now that we've figured out what's going on with our calcite crystal, let's change our focus over to our fluorite crystal, and we can determine whether or not our fluorite is isotropic or anisotropic by rotating it. So as we rotate the fluorite with crossed polarizers, we can see that not much of anything is happening. There are some cleavage traces and also inclusions that are lighting up in our fluorite, but overall, the whole crystal is remaining extinct as we rotate it. You can see the difference by comparing the fluorite as I rotate it to the calcite while it's transmitting light. So we did a variety of experiments today, but hopefully you feel comfortable now using a polariscope to identify a substance as either isotropic or as anisotropic. Our isotropic substances are not going to exhibit pleochroism in plane polarized light and are also going to remain extinct when we're viewing them with crossed polarizers. This is ultimately a result of the structure of these substances, which interacts with light in the same manner no matter the direction the light is traveling through these substances. Because of this, these substances can be defined by a single index of refraction. Our anisotropic substances are much more complicated with their interactions with light. Anisotropic materials can exhibit pleochroism when viewed in plane polarized light, however do not necessarily have to. These substances will, however, show the extinction and transmission of light with crossed polarizers, except for one or two directions through these materials that actually behave as isotropic substances do. These special directions are known as optic axes, and these special directions are going to be useful to us going forward for identifying anisotropic substances. The optical properties of our anisotropic substances are also ultimately a result of the structure of these substances, which interacts with light differently depending on the direction light is traveling through our material. Because of this, our anisotropic substances are defined by either 2 or 3 different indices of refraction. So going forward, we're going to further subdivide our anisotropic substances into those that are uniaxial and those that are biaxial. And our next video and kit are going to look at the uniaxial mineral corundum. So thanks for watching this video. Here are the references I've consulted in constructing this video. You should also note that there's a whole bunch more depth to optics than we're getting into here. We're kind of trying to keep things at the level where we can understand light in order to identify minerals. But there's a whole bunch more to learn. So once again, you can find the isotropic versus anisotropic kit from Snellius Minerals. The kit consists of a natural spinel crystal, a natural tourmaline crystal, a natural calcite crystal, and a natural fluorite crystal. As these crystals are all natural, each kit will be unique, but I'll make sure to test them out first myself so that there aren't any funny surprises when you try and go understand the optics of isotropic and anisotropic materials. So thanks for watching this video. If you have any questions, comments, or thoughts, please feel free to contact me at snelliusminerals@gmail.com. Our next video is Snellius Minerals Corundum Kit, and you can find the link for that here. Thanks again for watching, and have a great day.